assistant professor in the Department of Civil and Environmental Engineering at Vanderbilt University, where she is also the Little John Faculty Fellow in the School of Engineering. A really big deal. And we're impressed beyond belief with what Dr. Baroud has accomplished. And we are extremely happy to have her here today to discuss network resilience.
Thank you. Well, thank you all for having me. I mean, I cannot express not just my happiness to be here, but also my gratitude to this institution, to the Department of ISE, and then to Cash mostly. So you guys are extremely lucky to be in his class and to just know him overall. Okay, so what we're going to talk about today, we're going to discuss how we can use predictive analytics to quantify, to measure resilience of cyber-physical social networks. And probably by this time in the course, you have been very well motivated about how important resilience is, especially to infrastructures and communities. But I want to say something that could add to this motivation that you already have, is that NOAA every year puts together some statistics on how much disaster we've been experiencing. And so this graph here is showing a certain specific cluster of disasters that they call billion-dollar disasters. And so those disasters have been declared as having $1 billion or more in terms of losses. And so if you look at since the 1980s all the way to 2017, the increasing trend is very clear. Something is wrong. So not only are we having more events, but we're having more of very specific type of events, which is very severe events that result in major losses. And 2017 actually was a record-breaking year in the number and also the amount of losses that have resulted from that event. So when we look at this event with this graph, we start to think, are we doing something wrong? Is it, are we not developing the right tools to assess this risk, to be prepared? And so recently there has been a shift from risk analysis, risk management, kind of shift of thinking from mitigating against disasters to more recovering from those disasters. And so that's why people have started thinking about resilience, saying that, okay, these things are going to happen, now I just have to deal with it. I need to find a way to recover. And so that's why resilience engineering overall has become more popular in research. And so what I'm interested specifically in studying within resilience in my group, first is defining resilience, what it is. And it's very interesting. I'm teaching a course in statistics now this semester. It's called Risk, Resilience, and Reliability, because you want to make it look sexy for civil engineers to sit in a statistics course. So one of the things that we struggle with is defining resilience. So we know what risk is, we know what reliability is, but defining resilience can often be a big research question. Now that we've defined resilience, how can we measure it? Can we put a number to resilience, if we can quantify that resilience? Because we're going to take that and give it to the engineers who are going to design those systems or assess any infrastructure or community resilience. So we want to be able to put a number to it, to be able to measure it. Third question is, now that I've quantified it, can I predict the recovery behavior of a certain system or a community? If I can do that, then I can actually tell my stakeholders or emergency response managers how to allocate those resources before, during, or after a disaster. Don't worry, we're not going to cover all of these questions. Today we're just going to look at two of them. So first, how we can measure resilience, what type of metrics can we use? And then second, can I actually predict with some level of accuracy, if I have a system, can I predict how it will recover after a disaster? Looking specifically at networks, it becomes a little more challenging to assess resilience. The problem with networks is that there are multiple levels of resilience. So first you have your recovery of components, which are your nodes. So those could be facilities. Those could be clusters of people. Okay? The second level, you're going to look at the links that are connecting those nodes together. You're looking at roads that you need in order to recover some critical facilities. It could be critical substations in your power grid. It could be a hospital that is not receiving water. So you need those links. And then once you've looked at your components and your links, your nodes and your links, you want to look at the whole overall system level, and you want to be able to level up from the component base to the system level assessment of resilience. So how exactly do we do that? And assessing network resilience comes with a lot of challenges. The first one and most important is interdependencies. These systems do not operate alone. They are actually quite interdependent and linked, especially with the technology of communications and information sharing. These systems are becoming more and more connected. And so when we're looking at impact or restoration of one event, of one infrastructure, we're not only looking at impact on that particular infrastructure, so let's say the power grid. I'm not looking only at restoration of the power grid. Restoring power means restoring a lot more things. And these things could be hospitals, could be water distribution networks. It could be simply customers that need drinking water to go through their houses. And so not only when we lose power, we're losing more. Actually, when we recover power, we are recovering more. And if you remember Hurricane Irma, some of the deaths, actually, the casualties were not due to the hurricane itself, but it was due to the loss of power to some very critical facilities. Another challenge when it comes to network resilience within the context of infrastructure and community is, how do I assess community resilience? So we have those physical structures, we have the cyber technology that is connecting all that information, but all of this sophistication is to actually serve the people, the community. So how do I assess if I'm doing a good job or not? What do I use in order to do that? And so, along with some faculty and other students at Vanderbilt, we are interested in answering that question, so we came up with this paradigm to assess the community resilience, looking at the different capacities that a community has to achieve objectives, okay, in order to be assessed as called a resilient community. And so we have this hierarchical structure of these capacities going from survival to well-being and then planning for long-term viability. And so this paradigm actually not only helps us to put them in a hierarchy, but also look at the temporal effect of these metrics. Speaking of metrics, we're looking at resilience indicators, social resilience indicator. We went to the literature to see what's going on there. And we found more than 500 different types of indicators. It was really overwhelming. The qualitative analysis of community resilience was pretty overwhelming. So we brought it down to a foundational set of about 100 indicators that were categorized according to that paradigm, but also divided into different fields that correspond to these indicators. And so today we're just going to focus on the survival, and we're going to look at survival, social resilience indicators with regards to power and energy. So how many people are impacted by disruptions from the power and disruptions from the water distribution. Third challenge, data, which is what we're going to focus mostly on today. So data, there could be enough of it. Sometimes there's a lot of it. When it comes to resilience and recovery, there's not enough of it. And one of the reasons could be related to the nature of extreme events. There's not a consistency in the way recovery data is being collected. And so that results in a lack of historical data to look back and see how recovery measures were taken. And it brings a challenge to measure and accurately predict community resilience. Now, on the other hand, we might have a situation where we actually have a lot of data. And we want to be able to be ready, although we may not have that at our hands today necessarily. But technology is evolving really quick, and we want to be able to be up to speed to that technology. So in many cases, we could be using sensors to understand very important aspects of our system. How can we use that data to improve our modeling? The whole initiative around smart cities, getting infrastructures to communicate across each other. How can we leverage that information to improve the way we predict recovery? And so the goal of this lecture is to look at different predictive analytics models that can help us address these challenges with respect to measuring resilience, and especially looking at challenges of data. When I have a lot of data and sometimes I have not enough data, how can I leverage that information, account for uncertainty, and go back to the stakeholders and give them some pretty good accurate metrics for the recovery process. We're going to use Bayesian methods, Bayesian modeling, to assess critical infrastructure and community resilience metrics. And the goal of these methods are to assess uncertainty in the data and in the parameters that we have. The goal of doing so is to eventually come up with some form of a probability distribution for the performance of the entire network, whether it's an infrastructure or a community. So I'm going to tell you kind of generally what the case study is going to be, and then I'll go into the detail that'll give you kind of an idea of the general outline of the lecture, and then we'll talk more details about the model. So the case study that I'm going to use with the models that I'll present today is focused on an area in Tennessee. It's called Shelby County. It has a population of approximately 1 million, and it has an interesting mix of urban and rural areas. Memphis is there, which is the second largest city in Tennessee, and there are a lot of other smaller towns that are quite rural. The concern for Shelby County is mostly related to earthquakes, floods, and storms because of its location and because of the many rivers that flow through the county. It's a very interesting case study. Why? Because the utility over there, the utility company actually services the three infrastructures: the water, the power, and gas. And it's the same company that overlooks this. And then today we're going to focus mostly on power and water resilience to natural hazards as they relate to the community, since these are services that are quite critical to the community, so they have direct impact on the community. Now, why Bayesian reasoning? Besides that it's my favorite, Bayesian reasoning is extremely important. The statistics that you may have seen mostly in school focuses on the frequentist reasoning, where you have a set of data and you have a model that will model exactly what the data is telling you. Nothing more, nothing less. What Bayesian reasoning comes in and tells you is it will say that, okay, maybe you have some information about that data or about that process before. Or maybe there's some uncertainty in how the data was actually collected. How do you know? How do you account for that uncertainty? Let's be more flexible and let's add some bounds to that instead of just giving a point estimate that is just looking at the data and nothing more. Okay? So that way you can actually talk to people about their knowledge, you can incorporate that knowledge, but also you can understand kind of comprehensively what is the comprehensive set of potential estimates for whatever metric you want to estimate. So it's a pretty flexible tool, and it has been shown to work pretty well. So Bayesian methods in general have been founded on a very simple theorem called Bayes' theorem. And you probably have seen that in an introductory to statistics class, but it will just refresh your memory. So essentially you start with what we call a prior distribution, and this is your prior knowledge. This is what you, or maybe an expert in the field, or whatever information you have on your parameter of interest data that you want to estimate. Then you collect some new data, you have more information, and you have the ability to actually update that knowledge, update your probability distribution given this new information that you have. Why is this important, especially in disaster recovery? Because information is evolving as we are moving through the disaster. I may be getting more information on maybe how many crews I have, or I may be getting more information on the vulnerability of the communities that are being impacted. I want to be able to, every time I make an estimate, question myself and say, is this correct? Could I collect more information and improve that estimate? I want to have that flexibility. So where did this all come from? We'll just have a very quick history just to see where that came from. So essentially, Bayes' theorem is called Bayes because Thomas Bayes is considered to be the founder of that theorem. Although he did not really found the actual equation, what happened is that, so he was a reverend in the UK, and he actually wrote an essay to respond to a problem set that was proposed in a book. And so the essay was towards solving a problem in the doctrine of chances. And so he essentially solved a very special case of Bayes' theorem. But that essay was not published until 2 years after he actually died. And the person who published it was Richard Price, who actually found the essay, edited heavily, and then published it to the Royal Society. And so that's how we have a generalized Bayes' theorem, based on which a whole field of statistics is now built. And it has been extremely impactful in the field of sciences and other fields as well. It was used to break the Enigma code in World War II. It was used to assess a wide number of treatments for different diseases. And it's also being used to suggest movies for you on Netflix. And so it has a lot of applications. And we want to see if we can use Bayesian methods or improve on the way we've been doing resilience analysis using those tools. So to your left here, you'll see kind of a graphical representation of that same theorem that I showed you earlier. So essentially, you just have your data and then your parameter of interest, and you're updating that parameter based on any new information that you are receiving. One way we can extend that is to actually add another layer of priors on top of those priors. Why? So if my theta was my prior parameter, normally if it's a regular Bayesian model, I would just be assuming what the value of that parameter is, okay? Or I could make some estimations, or I could talk to someone who is an expert and try to elicit the value of that parameter, okay? But I have uncertainty underlying in that process itself. And so in order to overcome that problem, hierarchical Bayesian methods were extended from the Bayesian method to account for this uncertainty. So essentially, you add a prior to the prior that we call a hyperprior in this case, okay? Now, the true strength of a hierarchical Bayesian model lies in the ability to use more data than what you have. What does that mean? If you're looking here, the data that I would, if it was a regular Bayesian model, the data that I would be using to estimate my theta 1 would be lying in Y1, okay? But if I have a hierarchical Bayesian model, then I have this common hyperprior that is overlooking the rest of the prior parameters. And so in other words, if you work out the math, which we're not going to do that today, but if you do, the estimation of each of those individual parameters under each of those clusters ends up being a function of your entire data set. So if I imagine, let's say I have a big community and I'm looking at, let's say Shelby County, I'm looking at clusters of information, definitely I'll find more information in Memphis than I will find in the other smaller towns. And so if I have a situation like that where I have clusters where I have a lot of data set and then others I don't have enough data, the hierarchical Bayesian model will allow me to actually use all of that information to produce more accurate results, because now I'm using more data than I actually have in each of those clusters. And that process is called strength borrowing. So I'm borrowing strength or borrowing data from the other clusters. So far, when we looked at this model, what we have so far is just looking at the parameter of interest. So say if the parameter of interest was recovery rate, I'm just looking at historical data of recovery rate. I have not included any further information of what might impact this recovery rate. So if I want to add any predictor information or attribute information, we introduced kernel functions. And so we integrated Bayesian kernel models with that hierarchical model in order to kind of keep that nice property of strength borrowing, but also be able to add more information from other predictors. So the way Bayesian kernel models work is that this is just a regular Bayesian kernel model, so not a hierarchical one. So you have your prior parameter. Your parameter of interest is lambda. Your prior parameters are alpha and beta, okay? And your data follows a Poisson distribution. So I'm interested in estimating lambda, which is the rate of some sort. In our case, we'd be interested in the recovery rate. And in this case, instead of the posterior parameters being updated solely on your data that you collected on the recovery rate, they are a function of your prior, your historical data, and any further information that you collected. That third component, which is the information that you collected, is that kernel function k that we have here in the estimation of the posterior. And so think of the kernel function as some sort of a measure of similarity, where if I'm looking at my data set, it will allow me to say if I have, let's say, we'll talk in more details about this, but if I have some training set that I'm using to train my model, and then I get a new data point that I want to estimate, then I can use that kernel function to assess how that data point is similar to the data points that I have already in my training space, and then allocate the estimation accordingly, okay? So essentially, if this is my data set here, generally how the kernel function works is that it will map the data to a higher dimensional space, and it will allow me to understand any potential separation or classification between classes or clusters in that higher dimensional space. So in other words, it will allow me to identify nonlinear relationships in my data, okay, that are normally not detectable in my sample space here. So if you see, when I mapped it into the higher dimensional space, I was able to find that plane that is separating between those two. But in reality, if I go back to the original space, it was a circle, okay? And so I use this technique in order to avoid having kind of a constraint on the type of relationship between the predictors and my response variable, which is, again, is the recovery rate here. Then I get my hierarchical Bayesian kernel model. So I have the hierarchical structure. Okay, so I have lambda as my parameter of interest. The hierarchical structure is imposing a hyperprior on those prior parameters. And then any data that I collect on the characteristics of the system or the event gets integrated into the kernel, and that goes into the estimation of the posterior distribution. Now, there's a trick here that will make your life much easier computationally, and it's called the conjugate prior. That's something that I did not mention when I first introduced Bayes' theorem. It's essentially, there are certain pairs of priors and likelihood functions that work really well together. And so if you have a specific prior and a specific likelihood function, you're going to get the prior and the posterior following the same distribution, okay? And the parameters will be only updated with respect to the historical data and your predictors. So this is nice because you will have a closed form solution for your predictors. You don't have to run any simulation that will take a really long time. This is important. Why? Because in a disaster, I don't have 8 hours to run a simulation and then update my results accordingly. The other thing that I want to mention is the type of the kernel. So a kernel function could take any form. And in this case, we are using the radial basis kernel function because it has a lot of nice properties. And so the formula is at the bottom down there. So it's essentially, it's based on the Euclidean distance. So I could easily tell how close the points are in the higher dimensional space. The other nice thing is that it has only one parameter for estimation, which is sigma. But really, you can use any kernel function you would like. Now, in order to assess how well our model is, generally you would do some form of a cross-validation or some holdout analysis, meaning that you would train your model on a training set and then test it on a separate validation set. Except with these types of models, we need to add another a layer here, which we call the tuning set. And that tuning set is generally used to tune the parameters of the kernel function. And you would use whatever objective you want to tune those parameters. In this case, we use the root mean squared error. So we pick the sigma such that it minimizes the root mean squared error. Okay? To see how that model works well, in every new statistical model, you want to compare it to either similar models or just more classical that are methods that are more commonly used. And so in our case, we compared it to the generalized linear model, which is a very common method that will assume that the log of the rate has a linear function with any predictors. And so that's a frequentist method, for example. You have your data, and then you estimate your parameters, the theta naught and theta 1, or however many you have, depending on how many predictors you have. But there's no uncertainty. There's nothing probabilistic here. Okay, so you would have a point estimate in your prediction. We also look at hierarchical Bayesian regression model. So regression GLMs would take a GLM and then impose a prior on the thetas, okay, on your estimators. A hierarchical Bayesian regression will essentially have a hierarchical Bayesian model on those estimates, on theta i's, okay? And so in that case, you have your data here, and this is your estimates, and then you have your hyperpriors on top of those priors. So we use those two methods to check how well our model is predicting the data. So we used real data. Again, Shelby County was our assessment case study. And so we looked at power outage recovery predictions Of course, there aren't many events. As much as we would like to have more events, I don't think we want any more disasters. So we have to work with a small sample size. And so we take data over the last 10 years for all the storms that occurred. And that data was collected using Twitter feeds of the company and any news releases. So they usually just broadcast news releases on how many people are without power at certain time interval during the storm. And we focus mostly on the 5 most impactful storms. So here this is showing the recovery rate of communities of people without power, okay, as a function of time after a storm in hours for the 5 most severe storms in the county. To assess how well the model performed compared to the other methods, we compare it again to the other 2. So HBRM is the hierarchical Bayesian regression, and then GLM is the generalized linear model. We also look at what we call no model, but this is essentially a mean-only model, meaning that I'm assuming no information about any predictors or any historical data or any uncertainty. I just use averages to predict the future potential number of people without power. The metrics that we use to assess how well the model compares, the log likelihood, which we want to maximize because it's telling me essentially how well my model is going to predict given the data that I already have. And then the root mean squared error, which is a squared measure of discrepancy between the observed and the predicted value. Take the root mean squared, the root of that, square root of that. Now, if we want to look further into these errors and further compare the models, what we could do is we could look at the distribution of those predictive accuracy metrics. So this is the PDF and corresponding the CDF of the log likelihood. And you can see this was evident from the averages that they're quite similar. However, for the root mean squared error, the distributions are quite different. And we saw that the averages also were quite different. So if you look at the PDF, we can see that this is the GLM here in the black dotted line. It's quite concentrated. There's not much spread, but it has a kind of a longer tail than many others. HBKM and HBRM, so the red one is our model, which is the kernel one. And then the blue dotted line is the hierarchical Bayesian regression model. They're quite similar, but you can see that they are both actually to the left of GLM. So they have smaller errors, and their tails are much more controlled than GLM. If we want to look at the CDF, it would be much more difficult to distinguish between the errors, and we can see that things kind of shift in terms of the ranking of those distributions after a certain value for the RMSE. Okay? So in order to rank these probability distributions, we cannot really decide which one is dominating the other. We look at what we call a second-order stochastic dominance, which is a pretty simple method that would take the CDF, you would integrate that CDF. And so in this case, if we want to compare 2 CDFs, one for x and one for y, you would say that x has second-order stochastic dominance over y if the integral of x is less than the integral of y across all the values. Okay? So if you have a rational decision maker, meaning that they don't necessarily have a very extreme risk preference, higher values of x are preferred, then x would consider to have a second-order stochastic dominance. Okay? So in this case, for example, if it was a log likelihood, x would be preferred. If it was an RMSE, y would be preferred. So we do that for both the log likelihood and the RMSE. For the log likelihood, remember, we want larger values of the log likelihood. So the lower distribution is the one who dominates. And so in this case, the red one, again, our model HBKM dominates. In the case of RMSE, we want the upper distribution is the one that dominates because we want smaller values of RMSE. But we can see that around value 200, for RMSE values that are less than 200, actually HBRM is the one dominating. So HBRM tends to perform better for smaller values of errors. But in the case where we have large errors, HBKM is performing better. So it's able to kind of control those really extreme values for the estimation. So we look at comparison between the observed and the predicted. So this is essentially plotting. For the top right plot is the HBKM. So you have the x-axis, the observed value, and then the y are the predicted values. We can see that same phenomena that I just described earlier. So for values that are larger than a certain threshold for the observed value, you have better predictive accuracy, whereas for the hours that are closer to, for smaller values of the recovery rate, the model has a tendency to overestimate the true value. Okay? And then the graphs below are respectively the HBRM and GLM. So we can see that a similar phenomenon is shown here, but it's a much higher value for the recovery rate until we get that that accuracy. And then GLM is a lot less predictive than HBRM. Okay? So in other words, as we are progressing in time after a storm, we are gaining more information, and we are able to control that uncertainty around the estimation. And so that's why our estimates become more and more accurate. Okay? But oftentimes, it's really extremely important to be able to allocate those resources at the beginning of the storm. And so it's also important to be able to make good predictions when those values are small. And in our case, the errors when those values are small are still better than the one for HBRM. So how can we use that in decision making? Why is it important to have a Bayesian model versus other tools? The nice thing is that if you want to predict, let's say, the recovery rate at each point after a storm, normally you would have potentially a point estimate if you were using a non-Bayesian technique. Whereas when you're looking at a Bayesian technique and you're accounting for all this uncertainty, you actually have a probability distribution at each point in time. And so we're showing here kind of how that probability distribution is changing as the time is progressing after a storm. And if you look kind of in the upper right corner, you can see that the distribution has become tighter and tighter, which is showing that the uncertainty now has become less and less, and we have better predictive measures. Whereas at the beginning of the storm, there's a lot of uncertainty on the information that we are gathering, and so the distribution is flatter, resulting in a lot of uncertainty, and so that's why we are much further from the true value. Okay? And so depending on how accurate our estimates are, we can actually improve the way we allocate those resources, and we can also improve how much we are spending on recovery crews. So for instance, if we know exactly usually how our system recovers, then we know when exactly to call in for potentially resources from out of state, or from, so say a utility company would be interested in using help from FEMA to address recovery allocation. So when we know such information very accurately, we are able to allocate those resources more effectively, and we would be able to decrease the cost of logistics as we have more accurate predictions. Okay, so what we did next is we took this framework and generalized it into a methodology that we can actually apply to different infrastructures and communities. And so the framework here, essentially, you would have y would be your parameter of interest, which is essentially a joint probability distribution of x1 through xn. These xi's could be components, and y would be the joint distribution of your entire system. They could be clusters in your community, and you want to assess the overall community, but also keep those clusters separated. Or they could be representing a certain type of flow information in the cyber technology part of your network. Okay? And so for each of those clusters now, with the hierarchical framework, we have our prior parameter and then the corresponding priors, hyperpriors. And you don't need only to have just one layer. You can add as many layers as you want for the hierarchical model, but keep in mind that this might make your computation much more difficult and much more lengthy. So I'll show you kind of one example of how we use that framework here to estimate water distribution network performance So normally the number of pipe breaks is modeled by a Poisson distribution, which is a function of two parameters, RR, which is the repair ratio, and is usually estimated based on historical recovery rates of pipes, breaks per 1,000 feet. Okay? And then L is the length of the pipe. And so RR historically has been proposed by American Lifeline Alliance as a linear relationship between the hazard intensity and K, which is a parameter that is expressing information on the characteristics of that system. Now, generally, the intensity of the event has been developed for specifically seismic hazards, and so that intensity is normally expressed as PGV, for example, for earthquake, okay, which is peak ground velocity. But in our case here, we're using a generalized form where IH could represent any form of intensity. That way, if we want to model the system resilience to, let's say, flooding, we could use floodwater depth, for instance, as one of those intensity. Or if you're looking maybe hurricane, that could represent the category of the hurricane. So you can really think of any type of intensity. And so as I said, in this particular case, we're looking at water distribution. So K is determined by pipe material, pipe diameter, soil condition, and so on. As many characteristics as you'd like to represent the system. And so these parameters historically have been used kind of just a regression model to estimate these parameters. So A and K are usually used as constants. So they would use historical data, estimate kind of a linear regression based on what you receive as A and K. Then you would look at multiple intensities of that event, and then you would update your recovery repair ratio accordingly. So within this framework, instead of assuming that A and K are constants here, we assume that they actually are uncertain parameters, because there might be uncertainty in either the data that was collected or potentially the knowledge that we have about this parameter. So using distributions of the PGV and using distribution of K, we are actually able to generate a probability distribution for each component in that water distribution system. And then using that distribution, we can propagate that to the entire system, and we can probabilistically describe the system performance to a number of hazards. So this is essentially how A and K are usually estimated. So this is representing 81 data points, and then you have your linear regression, and the parameters are accordingly estimated. And so what we want to test is, if we have new data about the actual repair ratio, can we update our knowledge or our probability for the network performance overall, okay? Or let's say the utility company is interested in investing in a new technology, potentially placing sensors along those buried pipes. You are able to assess the health of those pipes continuously in time. How do you incorporate new data that you are getting to assess the potential probability of failure of your system, okay? And so kind of a quick, small toy example to show you how would that work. So this would be the distribution of the probability of failure if we assume a constant parameter, okay? And then the error around the PGV is random. And so essentially we'd have a distribution of the probability of failure, and your expected probability of failure would be essentially, for the entire system, would be 1 point estimate, which is shown by this vertical line in the middle, okay? If we use the Bayesian framework, then we are able to take this prior knowledge of the probability of failure and then update it with new information that we might receive, again, either from experts or potentially from technology that is installed within the system. And so the red distribution here presents the posterior distribution. And so the more samples or the more data you get, you'll get a more accurate estimation, a more accurate posterior distribution of that failure. Now, because I'm using a Bayesian framework, instead of having a point estimate for that expected value of failure, I can actually have a distribution for that expected probability of failure, okay? So I can understand the uncertainty around my estimates for the performance of my network. And so there are many other applications that we can use. Again, very generalized framework, and you can manipulate it however you want and apply it into either physical structures or cyber technologies or social, or in many cases, all three integrated together. Okay? So some concluding remarks on where we're going next with this. So we want to incorporate information on demographic data for the communities. So right now what we do is we understand how the infrastructure is recovering, but we want to see if there are any potential clusters in the community that are more vulnerable to disruptions, or that are actually able to recover faster than others. That would actually help emergency responders send crews to maybe small clusters in the communities that need more help than others. Okay? And so we, in addition to our information that we have from the utility company and the social media, we're looking at census data to assess any demographic information and integrate that in order to enhance the predictive accuracy of that model. So just to tell you what exactly we mean by that, we're looking at the social vulnerability index that is very well developed and is composed of a number of indicators, social indicators, that are looking at different demographic information for these communities. So this is showing just the overall indicator, which is including all those smaller indicators for the vulnerability. So the higher the score means that the community is more vulnerable. So the darker the color shows more vulnerable communities. For Shelby County specifically, we're interested, we noticed that a certain trend, that kind of three specific indicators that are heavily impacting how the social vulnerability indicator is calculated. The first one is the education level. So this is showing essentially the percentage of bachelor degrees earned across the county. Socioeconomic status is shown here in terms of median household income. And then the interesting one is communication skills. And so this one here, the darker the color, the higher the percentage of people who do not speak English well, which is extremely important for emergency responses and evacuation. We could be, developing very important measures, recovery measures for these communities, but if we are not able to communicate them well with our community, they won't be very useful. And so this is an extremely part of understanding the social aspect of the resilience of networks to enhance this recovery process. Some concluding remarks. So as I mentioned, network resilience, you have 3 levels of assessment. You have your components, your nodes, your links, and the overall system level performance. Why Bayesian methods are the best, I'm going to say in quotation, but the best in this case to model resilience. One, because they do a very well job of addressing data scarcity problems, especially that this is a big challenge we have in resilience measures and recovery data. 2, because they allow us to account for any uncertainty in our data and parameters, so they're quite flexible. We can look at ranges instead of just point estimate and move on with it. And third is the most important thing, is that you can include your stakeholders with the model. So it's not just a black box. You can actually work with those emergency response people. You can work with the person who is in charge of the reliability in that utility company. And you can refine that model as you are getting more information and more knowledge from these people. And then finally, predictive analytics, today more than ever, has become a big component of resource allocation. It's seen as a very important input to optimization and decision-making frameworks, so that these resource allocations are actually informed by data rather than assumptions about how the system works or how the parameters are determined. And so this is mainly what I have. I'd like to acknowledge the National Science Foundation for funding part of this work. Thank you.